Hello, can you hear me now?
Yeah.
Yeah.
Okay,
We
I was
can hear
afraid.
you.
Okay, I was afraid I was afraid I clicked on the wrong button. Okay, so you see the desktop, right?
Yes.
Yeah. Okay. Yeah. At first, I think I clicked on the wrong thing. All right. So all right. So we're going to continue talking about ML. There's a new reading assignment. The next chapter in the book. I mean, this is the PowerPoint from. It's not the actual chapter, but it's a third. The chapter is a third look at ML. Okay, and we'll start talking about that on Thursday. Today we're going to talk about some more examples of recursive functions. But the most important thing in this chapter is this higher order functions. That's mainly what the chapter is about. Something called higher order functions, which is one of the key ideas in functional programming and modern, I should say modern programming in general. So it's a real important idea. So that's what we'll spend a lot of time talking about, these higher order functions. Okay. And what we want to do today is go back to these recursive function examples. Okay, and I'm going to download them, and we're going to do a few more examples in this file. Okay, these are pretty good. It's a pretty good collection of it's a good collection of styles of ways of doing recursion on lists. Okay, it's almost all recursion on lists, and it gives you a good variety of examples of recursion on lists. So we're going to do today a couple of them. Last week before break we did the basic examples. Today we'll look at some of the more slightly sophisticated examples. Now remember, you have a, a programming assignment due a week from today. Okay, and this assignment is more recursive functions. Okay, so if you have questions about the homework assignment, send me an email. But the the the, the examples we're looking at are very much the patterns that you need to solve these problems. Okay, so these problems, I mean, the problems aren't on this page. You have to open that file to see the problems. But the problems themselves are very, very similar to the examples we're doing today and that we did last week. Okay, so let me download the zip file just to have it there. Okay, maybe we'll look at some of those examples after. Okay, all right. Now, here's the example of recursive functions. Okay, want to start with example 11 today. Okay. All right. So all of them are written in a similar style. They give you here's the uh, type of the function that gives you a sense of what it should do. It takes in a list, a polymorphic list. So the function doesn't care what's in the list. If it's a list of integers, a list of strings, but what it's supposed to do is take the list and produce a list of pairs. Okay. So it's going to take in a list and produce a list of pairs. And what it's supposed to do is it's supposed to take the first two items in the list and make a pair out of them. Then take the next two items in the list and make a pair out of them. So take the first two items and make a pair out of them. Take the next two items and make a pair out of them. Okay. All right. So it's pairing them up. And if you give it a list with, if the list has an odd number of items, the last item kind of gets dropped. Okay. So the last item, if there's an odd number of items, the last item won't get paired up. Okay. Oh, and there's yeah, see, that shows, see, if there's only one item in the list, then you produce the empty list. Okay. Now, what's different about this is that we need two base cases for the recursion, because here, watch what this happens. If we're given an empty list, we should return an empty list. Okay. On the other hand, if we're given a list of one item, we should produce the empty list. That was here and here. Now we need both those base cases, because what do we do otherwise? If we don't have the empty list or one list, we have two items in the list. So we take the two items off and recurse on the rest of the list and take the two items and make them in a pair. Okay, so if you have nothing in the list, return nothing. If you have one item in the list, return nothing. If you have two or more items in the list, take the two items, make them a pair, cons that on to now recurse on the rest of the list. Okay. Now, let me put this into ML and then we'll play around with it a little bit. Okay. So, okay, I can just, okay. So now it's defined in ML. So yeah, now I can pair up, a list 1, 2, 3, 4, 5, 6. Oops. Oh, I was writing a mixture of ML and Java. I used yeah, I used a parentheses like if I was typing Java, but it's a list and you don't use any parentheses. So call the function with this input, which is a list. Okay. So it's, when you switch between languages, it's real easy to get goofed up a little bit about the syntax for them. Okay. So do I have an extra comma or something? Oh, there. Okay. I was at the wrong prompt. See, I typed it in at the wrong prompt. I was still stuck in this prompt where I had messed up something here. See the prompt there? This was all the continuation of that same prompt. The equal sign is a continuation of a prompt. So that means that it didn't finish, it didn't think this was a complete line. So it asked me to finish it, I typed in a semicolon, but that still didn't close it. But then when I typed in this stuff, it did close that, but it was an error. And then there's the new prompt. Okay. So when I typed this in, I thought I was typing into the prompt. I didn't look carefully. I was still continuing that prompt there. So all of this was one input, and that's what this error message is about. Okay, so somehow by putting a parentheses there, I never closed the parentheses. So the semicolons kind of just didn't close anything off. Okay, so now here was the right input. Okay, and pair 1, 2, 3, 4, 5, 6. Okay, and notice I'm getting out a list of integer pairs. Okay, and I could do this with it's a polymorphic function, so I could give it a list of strings. It's more. That's the beauty of polymorphic functions, is that I didn't have to write one version for integers and one version for strings. Yeah, it works for both. We write it one time. Now you have to compare that to like when you first learned Java. You learned to, for example, instead of having lists, you used arrays a lot. But every time you write a function for arrays, it only can really work with one kind of array. You can find the max of an integer array. Then if you want to find the max of a double array, you have to write another function, find the max of a double array. Then if you want to find the maximum in an array of strings in alphabetical order, you have to write another function. And there's nothing polymorphic about C and Java arrays. They're like the most unpolymorphic things you can work with. Now, ML is trying to improve on that. It's trying to be able to say, well, if you write a function, it should work on lots of different things. You shouldn't have to keep writing functions over and over again. And Java does the same. Java moving away from arrays. Really modern Java programming isn't going to use arrays anywhere as much as it did 20 years ago, because there's absolutely nothing but polymorphic about array. It's harder to work polymorphically with arrays. It is possible, but it's more difficult. Okay. So here, this thing is, ML is designed from the ground up to be, in this sense, polymorphic. If you think about this function, it doesn't need to know what's in the list. Its job is to say, if you give me a list of things, I'll pair up the things into pairs. That might be a data processing step. This is the kind of function that can be part of a data processing step where you're given a bunch of numbers and you need to, like maybe they're actually coordinates of points, but they're given to you in a list like this. It's not unusual at all to have data in long lists, but the data is actually meant to be grouped, like those two are coordinates of a point. Those two are coordinates of a point. Okay, so a function like this would group the data for you. Okay, but it doesn't really need to know what kind of data it's working with. It can be polymorphic. It doesn't really need to know that it's a list of integers. Okay, now let's play around with this and see why we need these two base cases, because this is a good example to think with. Okay, what I'm going to do is take this example. Like it says down here, take the above example and remove. Okay, I'm going to follow the instruction. Take the above example and remove from it the one line base item. So remove this base case here. Okay, so now take this function and put it in ML. Oh, no, I got a non-exhaustive match warning for one thing. Yeah, because I didn't handle that one. Notice that the function's got a problem now. It actually is missing. Okay, and the compiler warned me about that. But I'm going to ignore the compiler warning. I'm going to say, well, let me test the function. Okay, there's one of my test cases. Well, there's one of my test cases. It worked fine. Okay, didn't seem to have a problem. Okay, here's another test case. I'll extend this one a little bit. Okay, it's working. Yeah. Yeah. Well, what's the problem? The problem is, what if I give it a list that has odd length? See, now it blew up on me. I didn't get a right answer. Okay. See, the list has odd length and it caught an exception. It threw an exception. Because what happened? It paired up those two, then recursed on what's left. Then it paired those two, then it recursed on what's left. And that gave it the base case that we skipped. We're going down by twos, and we end up with this case here, not of the empty list, of a list of one item, and we're missing that base case. So this version of the function works fine on even numbered lists, but not on odd numbered lists. Because we're going down by twos, when we go down by twos, if you start with any number and you go down by twos, you're eventually going to get to 1 or 0. Okay, but you may, you don't, after you, if you keep going down by twos, after you hit one item, you'll be negative one item, but you can't have a list of negative one items. So if you start with an arbitrary list and you keep lopping off two items at a time, you're going to get down to either a base case of one item or a base case of 0 items. Okay, like I could take this function and get rid of the empty list base case. Like try this one. Okay, take this one and like that. Okay, now it takes care of the one item case, but doesn't take care of the two item case. Now this version is going to work on odd length lists, but not work on even length lists. Okay. Oh, I didn't. Okay. Now the compiler is smart enough to give me a warning. Yeah, it notices that there's something wrong here, that there is that I haven't handled every possible input list. Like I handled a list of one item and a list of two or more items, but I didn't say what to do in a list of 0 items. Okay, now if I play around with this, it works fine on a list with 5 items. Okay, it'll work fine on, see, is this one the one with odd? That one's got an odd number of items and it works fine. Okay, but now it's not going to work on a list that's even length. Okay, see, now it blows up on a list that's even length. Yeah. Notice that this, one of the things this shows is that you have to really test your functions. if you don't test enough, you might be fooled into thinking that that you've got a correct answer. Now here the compiler was really warning us about what could be the problem. You don't always, not every bug has a compiler telling you that you've got a possible problem here. But at least even if we ignored the compiler warning, by doing enough testing, we'd see that this one has a problem on odd length lists, and this one has a problem on even length lists, because you're going down by twos, and so you really have two base cases. Okay. Now, if you go back up here, remember the top of this file was an outline of what we do to write recursive functions. We're writing recursive functions on lists. A list is either empty or something in front of the rest of the list. Or if you write it like in a grammar, a list is either empty or an item in front of a list. Okay, there's the recursion. See, a list is defined recursively in terms of list. You've got a base case, and then you've got a recursive case. Okay, now, but this is a little bit misleading because not every function you write on lists is going to have just two cases, a base case and a recursive case. We just saw an example that needs two base cases. Okay, we just saw something that needed two base cases because we don't recurse quite this way. So this is this is kind of an outline of the general idea of recursion, and it works for the most basic functions on list, but it doesn't work on every function on list. So if we pull two items out of the list at a time, instead of pulling one item, this is the definition of the list. Okay, so this is a correct definition. But when we write a function on a list, a basic function matches that pattern there. What to do on the empty list, what to do on a non-empty list. Okay, what to do on the empty list, non-empty list. Okay, see, that's written exactly here: empty list, non-empty list. But not every function is going to just work with one item from the non-empty list. Like we saw a quirky function that says, but if you have a non-empty list, pull two items out of the list. Well, what if you don't have two items in the list? Then you need a base case for one item. Okay, so this is the general idea of recursion. It matches the definition of what a list is, but then when you start working with arbitrary recursion, you get patterns that are a little bit different than this, patterns that are close to it, but not exactly the same thing. Okay, so there's one example, number 11, where you need two base cases, because in this case, it's because we're going down by twos. Well, now we're going to do some other examples where we need two base cases for different reasons. Okay, but in this case, we need two base cases because we're going down by twos. Now, if I wanted to, I can make this triple up function. Yeah, I can make this a triple up. Yeah, so I could take my pair up and quickly turn it into a triple up. Okay. Okay, so I'll triple up. Okay. Now for triple up, if you give me an empty list, I give you back the empty list. Okay. If I triple up on one item, I don't have enough to triple up, so I give you an empty list. And then I'll need a third base case, because if you give me two items, there's not enough to triple up. So if you give me two items, still empty. And then now it'll be, if you give me X in front of Y in front of Z in front of, say, Z's. So if you give me three items, I can triple up the three items and then recurse on the what's left. Okay. Now, I can do quadruple up, and then I would need four base cases. Yeah. Now notice that if you get this, you can't do, oh, I'll pair up that. Like this won't work. Okay. Suppose you say, well, okay, if you give me three items, I'll triple them up, but if you give me two items, I'll cons X comma Y You know, that's what I have, X and Y. So why don't I cons them onto the, oh, I have to finish this. Oh, well, if I'm going to do it this way, I have to have what's left. So I have to write it. If I want to actually do it that way, I have to write as X cons on to Y, cons on to Y's. Okay, so there's 2 items. So triple up on the Y's. What's wrong with this? Why isn't this a good compromise? You know, somebody can see what's going to go wrong if I try this. You give me white item, okay, I don't triple it up. You give me, you know, you give not. There's an empty list. There's nothing to triple up. You give me 1 item, I don't even try. If you give me 2 items, okay, why don't I pair them up and put them on the list? Then if you give me 3 items, I triple up. What's wrong with this as a compromise? Anybody see what's going to happen? It won't compile even. Then we see what's going to go wrong.
Will the last line even run?
Say again?
Will the last line even run?
This
Ever?
line?
Yeah.
Well, of
Because
course. Yeah. If you
because
give
the
me a list,
line,
pardon me?
I'm sorry, because the line above it will always fill the requirements for your list.
Oh, that's a good point. Yes. You won't, yeah, no, yeah, you're right. You'll never get to this one even. Oh, I didn't even think of that. That's real good. Because what happens? Like, think of an example. Okay, there's a list. Okay, so it's not the empty case. It's not this case. Oh, there's 2 items. So grab 2 items. Okay, and then you recurse on what's left. Okay, now what's left? Well, it's not empty. It's not 1 item, but there's 2 items. So grab those 2 items and recurse on what's left. Okay, then you have 5, 6, 7, 8. Well, it's not empty. It's not 1. Oh, grab 2 items and recurse on what's left. Okay, so yeah, you'll never get to this line. That's a good point. There's another problem. So you'll never get to this line, and there's a problem with this line. Okay, so that's real good. It will not even get here, but what's wrong with this line here now? Now tell me what's wrong with this line also.
Do you need parentheses, or does that matter?
Oh yes, I need parentheses. Yeah, so that's a syntax error. Now what's the logic error? What we're trying to do is write a function that looks like this. It should take in a list and give me back a triple list. See, so it should take in a list of A's and give me back a list of triples. So now what's wrong with this?
You're guaranteed at least 1 double.
Well, no, what's wrong with it? Yeah,
It's not all triples.
it's not all triples. Yeah. See, it's trying to mix doubles with triples, and the type system won't allow that. A list of triples doesn't allow a double in the list. Like go over here and let's try that in ML. Here's a list of triples. There's a triple. There's a triple. Okay. There's a list of triples. Notice I forgot. See how I forgot a parentheses. So this thing's out of balance. So the semicolon didn't really close anything. So it's still thinks that it's reading that one line of input. Okay, so ML's kind of, I goofed up, so ML doesn't really understand what I'm doing. Sometimes another semicolon got it out of that. Okay, what I need to do is go back to that line, and I needed a parentheses right there. Okay, so there is a list of triples. Now sneak a double in there, sneak a pair in there. Okay, so now ML's not going to like that because it's not a list of doubles and it's not a list of pairs. It's not a list of triples. It's a list that has a mixture in it. And ML doesn't let you mix things in lists. Okay, now the error message is pretty tricky to read, but basically it's saying here, see, it noticed that at some point that they didn't agree. You consed on a triple and you consed on a double, a pair, and you can't do that. If you have a list, you can't have a triple and a pair mixed in there. Like if I put the pair in a different place, I'll put the pair over here. Okay. Okay, now there's a pair in the middle of those triples. Okay. And you can see that the error message says, well, at this point, there's something wrong because you're consing two different things. You're building a list, and here's a pair consed onto a triple. Okay, so ML doesn't like that. Okay, so over here, this isn't going to make sense because another reason why it's not going to make sense is this is consing on a double and this is consing on a triple. You can't mix them up. Okay, so it doesn't make sense to say, oh, if you give me two things, I'll cons on a double, but if you give me three things, I'll cons on a triple. And also, you'll never get, so there's two things wrong with it. It's mixing types. It's sometimes consing doubles and sometimes consing triples. And it never actually gets to this one because it'll always see the first two items. Now, you could reverse the order of these. Okay. Now it's a little bit interesting. Now this would make more sense. Okay. Now, if it's empty, nothing. If there's one item, nothing. Oh, if there's three items, go ahead and triple them up. What if there aren't three, but there's two items? Now try to double them up. Okay, so this gets around the error that we never got to that last. Now all three of these lines will work. If you give it an empty list, one item list, one item list. A three item list, okay, you'll get your triple. Okay, but if you give it a two item list, it'll try to build a double, but this one won't compile. Oh, I forgot the semicolon there. Okay. See, it didn't like the pair const on to triple up. See, it basically said, no, you're supposed to be doing triples. Then all of a sudden you want to put a double on there, and it says, no, you can't put the double in front of the triples. Okay, so actually, let's go back to the way it was and try compiling that one. Okay, so a minute ago we had it with those last two lines reversed. We put this one back where it was. Okay, now this is the version that really doesn't make sense. You don't ever even get to this case here because you'll always find the two items before you even find the three items. Let's see what the compiler thinks about this one. It still isn't going to, it's got two things to complain about. It might notice that this pattern never gets used. So it might actually, I'm not sure which one it's going to complain about more. It could either say, here you're consing pairs and here's your consing triples, so that's a problem. Or it might say, you never even get to this pattern. So let's see which one the compiler complains about. It didn't like the type. See, since it saw this consing of a pair, it won't let you cons a triple. So it's decided that it's actually a function returning pairs. Okay. And it didn't like, see, it didn't like, yeah, it didn't like this one. Now it didn't complain about the, it did not complain. Oh, actually, watch this. How about that? What am I doing there?
Just forcing it to be a triple.
Yeah, forcing it to be a triple. So I'm now saying that, oh, if you give me one item, I'll give you the empty list. If you give me two items, I'll make it in a triple. I'll just put a 0 at the end. Now that's now now one thing, it's no longer polymorphic. Why not? What do I mean by that? It's no longer a polymorphic function. Why not? What do I mean? It's not a polymorphic function anymore. What have I how have I lost? What do I mean by it's not polymorphic? What have I lost here? It doesn't have this type anymore.
Does it have to be a triple of ints?
Yeah, because this guy is an int, and these are all supposed to be the same. See, they came out of a list. See, it's saying that you give me a list of anything, I'm going to give you back triples of that same kind of thing. But here, one of the triples has got a 0 in it. So that makes that integer. But all those are the same type. So now it has to be an integer list. Okay. So go over here. Now, what's this going to do? Let's see. Let's play around with this one, see what it does. Okay. Oh, I got an error. Match redundant. See, now it noticed that you don't ever get to line 3. See, there's the error message that says, oh, that, yeah, when you notice that, you know, there's the error message that says you match redundant. This guy doesn't do anything because you never get to it because you always find two things first. So if you're always going to find two things, you'll never find the third thing. Yeah. So this one now is a redundant case. Okay, so that's the kind of error message you would get when there's something that's redundant. Okay, now if I reverse them, it won't be redundant. Okay, now it's not redundant. If you find 3 items, use them. And if you find 2 items, use them and put the 0 at the end. Okay, so now that it moved it into the place where it's not redundant. Oops. Oh, I have to get rid of that semicolon. Yeah, when I move the lines around, there's supposed to be a semicolon at the end of the last line. ML is funny about semicolons. You get used to using semicolons in a Java way where you put a semicolon after every line. In ML, you put a semicolon only at the very end. So you don't put semicolons at the end of this and this and this. You put a semicolon at the end of the last one. This essentially is, this is one long line. And so the semicolon goes at the very end. Okay, so now let me put that over here. Now notice I'm at the equal sign prompt. So that means it's ML's kind of messed up. So let me just put a semicolon there and get out of, okay, so get out of that prompt, type in this function. Okay, now there's the loss of polymorphism. See, the function takes int lists and gives me back int triples. I lost the polymorphism by putting that 0 in there. Okay, now what does it do? If I give it a list, what am I going to get out? Oh, Well, I'm not going to get anything if I don't triple up. Think about what am I going to get out? It's going to triple them up. Well, actually, it depends on my list whether it has even length or odd length. Okay, or if it has if the length is a multiple of 3 or not. See, it's going to go down by 3s. So this list would have a length. So 1, 2, 3 should be tripled up. 4, 5, 6 should be tripled up. Oh, and then 7, 8 should get paired up with a 0 on the end. Okay. There. So the 7, 8 got paired up with a 0 on the end. Okay. So it notice that this is kind of quirky. I had to do a funny order to be able to triple up most of them, but only double up on a, when there's only 2 of them, I double up, but I have to come up with this dummy item here. But putting a dummy item in there made me lose the genericness of it because I had to cook up a 3rd item. And since I picked 0, then the function is no longer generic. Okay. Yeah. So you notice there's a lot of weird things going on here. I could either do it the right way and have 3 base cases. So let's go back to the, okay. Yeah, here's the right way. You know, this is what we really wanted. You know, base case of nothing, base case of 1, and a base case of 2. All those give you empty list, and then you triple up things. Okay. Here I'm trying to recover the last 2 things. Okay. If I recover the last 2 things, I can kind of do it by putting this thing last, by putting the 2 item case last and cooking up an item here. Okay. Okay. Now, here's a question. Is there a way to pair up the last 2 items and not lose the generic and not lose the polymorphism?
Just use
Just tell me.
Y.
Pardon me?
Just repeat Y again.
Yeah, so why not, instead of putting a dummy 0 in there, just repeat one of the items. Like, let's go ahead and repeat the Y. Okay, now let's see what happens here. We should get back the polymorphism now. Okay, see, we got back the polymorphism because we didn't cook up an arbitrary value. So now ML says, well, this will work with any types. Okay, and now if we do that example we did a minute ago, like this one, see, it tripled up it just doubled the 8. Okay, so it tripled up everything, and then when it got to a pair, and then what about, then you can say, well, if you like that idea, why not do the same thing with this guy? Okay, why not do something like this? If I wanted to, if I thought this was useful, I could take this case and move it to the end. Okay, and say that if I have a 1 item, okay. Oh, and notice that since these guys are at the end, I can actually, I don't have to even, since I'm going down by 3s, I don't get to this case unless I'm at the end. So I can actually do this one this way. And not have a recursion there. Okay. But return a single item list with that. Okay. And if you give me 1 item, I'll return a single item list with that item repeated 3 times. Okay. So there's a base case for 1 item, and this was the base case for 2 items. But now I kind of reverse their order. Okay. If you give me an empty list, I'll give you back an empty list. If you give me a list with 3 items in it, I'll triple them up. Okay. But if it's not empty, it's not 3 items. Well, if it's 2 items, but now notice I need to have this one after that one because otherwise this will catch the first 2 items. Okay. So if it's a list of 2 items, or actually, if I write it this way, oh no, this matches exactly a list of 2 items. So actually, I could put this one back at the beginning. I could put this one back before there. I could put this one. I can put this one back here now because it only matches exactly 2 items. So it won't collide with this one because this one will be 3 or more items. This will be exact. See, if I write it this way, instead of writing it with a cons in front of it, this says exactly 2 items. And this one says exactly 1 item. Okay. Okay. So now I'll be doing it as if it's exactly 1 item, return. If you give me the empty list, I'll give you back the empty list. If you give me a list with 1 item, I'll go ahead and triple it up. If you give me 2 items, I'll go ahead and triple it up by repeating the second item twice. And then if there are 3 items, I'll go ahead and triple up the 3 and then recurse on what's left. Okay. So this is another way to write it. Could write it this way too. Okay. All right. So there's but the key idea is that you may need more than one base case. Okay. You may need more than one base case, and you may need to think hard about how to order the base cases too. In more complicated cases, as we'll go down the list, we'll see that sometimes you have to be very careful about or you need more than one base case, and you might need to pay attention to the order of them. Okay. All right. So here's a bunch of different ways of doing tripling up. Okay. Now let's look. Here's something that's real similar to triple up or double up. The double up took a list, or pair up took a list and gave me back a list of pairs. It took in a list, it gave me back a list of pairs by taking 2 items out of this list and making them into a pair. Okay. Here's the next function is actually a famous function. It's built into ML called zip up. Actually, it's called zip. I called it zip up just to give it a different name. It's called the zip function. It's actually a pretty famous function. What it does is it takes in 2 lists and gives you back a list of pairs. Okay. Remember, this other one took in 1 list and gave us back a list of pairs. It took in 1 list and gave us back a list of pairs where you just took 2 items at a time out of this list. Now we're going to take in 2 lists as inputs, and we're going to produce a list of pairs by taking 1 item from this list, 1 item from that list, and pairing them up. Then take another item from this list and another item from that list and pair them up. Okay, so it's like a zipper. You think of this list and this list being zipped up by you take the first item of this and take the first item of this and pair them. Then take the second item of this and the second item of this and pair them. The zip function actually gets used a lot in data processing. So it's built into ML. It's built into Haskell. Okay, so let's write the zip function. Okay, now the zip function's got kind of it's going to need 2 base cases, but for slightly different reasons. Okay, so one base case is that one of the input lists is empty. The other base case is that the other input list is empty. I don't want to, what I don't want is a base case that looks like, I don't want a base case that says I have 2 empty lists. That's not a good base case because if you think about what I'm doing, I'm starting, like, let's do an example here. Here's a list, 1, 2, 3, 4, and I want to zip it with the list, say 1, 2, 3. Okay. I peel off this one and pair it with that one. Then I take this one and pair it with that one. then I take this one and pair it with this one. Now I take this one, this list is not empty, but there's nothing to pair it with here. So notice my base case doesn't end up with two empty lists. Now it would have if this one looked like this. Then this one is paired with that one. This one's paired with this one. You get to 4, it gets paired with 4, and then you have an empty list here paired with an empty list here. Okay, but you're not guaranteed to get to that. Okay, you know, if I have something like this, now this list will become empty when this list still has a 5 in it. So I can't say my base case is two empty lists. My base case could be the left list is empty, but the right list is not empty. Notice I've used an underscore here to say that I actually don't care what's in the right list. If the left list is empty, I'm done. Okay, I'm going to return the empty list. Because if you zip up the empty list with anything, there's nothing to zip. So if the left list is empty, I don't care what this one is. It may or may not be empty. I give you back the empty list. On the other hand, if the right list is empty, I don't really care what's over here. If you give me some stuff over here and you try to zip it up with the empty list, there's nothing to zip up because there's nothing in here. So if you give me the empty list here, I don't care what's over here. I give you the empty list. Now, what about this base case? Is it there? How does this one get taken care of now? They say, look at the code. Where does this one actually get handled?
Be the first one, right?
Yeah, be the first one. The first one says if the first one is empty, it doesn't care about the second one. So this line here actually handles the case of two empty lists, but you don't write a base case of two empty lists. Okay, which is especially when people are first starting with this. That's almost everybody's first thing is I'm recursing on two lists, so my base case is empty, empty. Yeah, so it'd be real common for people to say, "Oh, I start with the base case of being two empty lists," and you can do that. It'll actually, but you still need the other three. Then you would need three base cases. You would actually need three base cases. Suppose you actually did start with zip up with the base case of empty, empty. That wouldn't eliminate the need for both of these still, because you still have to worry about empty, non-empty, non-empty, empty. So even if now this won't be wrong, but it'll just be, ML might point it out that it's redundant. The compiler might, let's see if the compiler points out that we've got a redundant case there. No, it didn't even complain. It didn't point out. It's a redundant case that doesn't harm you, okay? Because this overlaps with this and it overlaps with this one, but they all give the same answer. So I think the compiler doesn't really worry about the fact that this is redundant, okay? But it's not a good idea to think this way. Instead of thinking, oh, my base case is two empty lists, that's not the right way to think about it. The base case is either the left one is empty or the right one is empty. There's actually two base cases. So let me go back to being the way it should be. It should be two base cases. And then one of those base cases actually takes care of that one. Okay, now, if you're not in the two base cases, you have two non-empty lists. This one's not empty and this one's not empty. So there's something in that one, there's something in that one. So you can pair up the two items and then you could zip up what's left. Okay. Now notice that this thing is polymorphic in an interesting way. This list doesn't have to hold the same thing that this list has. I can make this one, for example, over here, I can make this zip up 1, 2, 3, 4 with cat, dog. Okay. Yeah. There's nothing to stop me from pairing up these. 1 goes with cat, 2 goes with dog, 3 goes with apple, and the 4 just gets ignored. Okay. Yeah. And ML will realize that when I'm doing this, I'm not in any way making the X's interact with the Y's other than pairing them up. Okay. So there's nothing that says what the type of X should be. There's nothing that says what the type of Y should be. I'm not adding, I'm not subtracting, I'm not multiplying, I'm not doing anything with them other than pairing them up. So ML will realize that this thing has type. ML gives this thing a very generic type. We saw it over here. See, it gives it the type any list of A zipped up with any list of B gives you a list of AB pairs. Okay. So for example, let me do this one here. Zip up. Now I wrote it to take in a it takes in a pair of lists and it gives out a list of pairs. So I'm going to make the input a pair of lists. So I enter it like this. Okay. So I want a pair of lists. Okay. So zip up is given a pair of lists and then it gives me back a list of pairs. Okay. So notice it gives me back, in this case, int string pairs. Okay. If I go over here, I can change this to 1.1, 2.2, 3.3, 4.4, 5.5. Now it's going to give me back int real pairs. Okay, see, int real pairs. So it didn't care. Zip up will work on any kind of pairs. Okay, it'll work on any kind of list. It could be any list in here and any list in here, and it'll pair them up. Okay. If you Google zip function, let's see. Well, there's one in Python. I just Googled zip function. There's zip functions all over the place. Python's such a popular language that if you Google zip function, notice it's all Python, 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 Python. That shows you how popular Python is. Let's see. Now, zip function JavaScript. There is a zip function in JavaScript. Or zip. I don't know. I don't think Java has a zip function built into it. Yeah, you have to write your own zip function. Java doesn't actually come with a zip function. So you have to use somebody else's library or write your own. Okay. On your hand, ML. There's a zip function in ML. Okay. Or in Haskell. Haskell writes things differently. This is this way of saying a list of A's, a list of B's, and you get out a list of pairs of A's and B's. Okay. So the zip function is pretty common. ML has one built in, Haskell has one built in, JavaScript has one built in, Python has one built in. I wonder if C++ has one. Somebody else is asking, is there zip-like functionality in C++? You can write your own. Yeah, so I think in C++ you'd have to write your own. It probably doesn't come with a built-in zip function. Okay. Here's a zip function in the Boost library. It's a real famous library in C++. It's not part of the language. It's a separate library, but it's a library that lots and lots of people use. Boost is real famous. So there's a zip function in the Boost library. Okay, so zip is surprisingly useful. And it's real easy to write. It's only a few lines of code, but it's a surprisingly useful function. It gets used a lot in data processing. It's a way of taking two lists of data and pairing them up into tuples. For example, if you want to graph them, like if you're going to graph, this is a list of, like, you have a list of data and another list of data, and you want to plot them. Okay, you want to create a plot, and so you would use a zip function to zip them up into pairs, and then you can take the list of pairs and give it to a graphing function. So that's a simple example of zip. There's lots of other ways it gets used. So it's a real workhorse function in modern machine learning, data processing, data science. You see zip used a lot. Okay, and it's real easy to write. It's a really easy function to write. And it's a nice, elegant example of recursion because it recurses on two lists simultaneously. And so this is the pattern for recursing on two lists. This list empty, you don't care about the other one. This list empty, you don't care about the other one. Oh, you can put the order of these two in either. The order of these two lines doesn't really matter. So there's nothing special about making the first list empty first. So you could reverse the order of these two lines, and I don't think it has any effect on the definition that I can think of. Okay. Now here I'm peeling off one item at a time. Now I could do a really weird zip, like I could combine zip up with pair up. Okay, so here's kind of a weird thing to do. Okay, I'm going to combine zip up with pair up. So I'm going to do zip pair up. Okay, what I mean by that is I want to pick an X and a Y out of each list. X and a Y, and then I have to use I'll make it a U and a V over here. Okay. And let's see, zip up with pair up. What can I do to combine it? Then this would be the, okay. So I've got four things. I've got an X and a Y and a U and a V. I could do something funny like X paired with U, Y paired with V, and then those two paired up. A pair of pairs. Okay. So I pair X. Well, actually, if I did it the way it was before, it would be more, no, it'd be like this. X, if I actually was doing pair up, X and Y would get paired up, and then U and V would get paired up, and then that pair would be zipped with that pair. Okay, so there's the pairing up. Take two elements out of one list and pair them up. Take two elements out of the other list and pair them up, and then zip up the pairs. Okay, all right. Now, but now I need more base cases. See, now I would need now it needs to be, it's going to get a little confusing on the base cases. Okay. If they're empty, see, this is where you can come up with all kinds of interesting examples to just challenge yourself with coming up with how to do this. Okay, so now I want to pull two things out of each list at a time. Okay, so we'll do it like before. If there's, okay, if you give me the first item, if there's only one item in this list, I don't care what's in that list, I'll give you back the empty list. There's nothing to pair up. Okay, there's only one item in this list, so that's not enough. That's like we did before with pair up. With pair up, we said, well, if there is one item, don't do anything. Okay, you need at least two items to do a pairing up. Okay, so we'll do that here. Okay, so if there's one item in that list, okay, same thing over here. We have to do it the other way around. I don't care about the first list, but if the second list has only one item, I'll give you back the empty list. Okay, so I need 4 base cases. Empty list here, empty list here. There's nothing to zip up. If there's only one item here or one item here, I don't have enough to zip up. So if then here I have 2 items here and 2 items here, I'll pair up those 2 there. Now pair up those 2 there, okay, and zip them up, okay. Now let's see if that works. Notice that the function is going to give me out a tuple of tuples. Okay, notice that the output takes in a list of A's and a list of B's and gives me a list of tuples where the tuples are a pair of A's and a pair of B's. Okay, so what does this look like? Zip pair up of a list. Let's see, just wait, 1, 2, 3, 4, 5, 6, 7 with a list of say 1.1, 2.1, 2.2, 3.3, 4.4, 5.5. Okay. Okay. Now let's see. That should pair. There's 2 items out of this one, 3, 4, 5, 6. This one's got an odd number length, so this 7 is not going to have anything to pair up with it. And this one, I think I made even length. 1, 2, 3. Yeah. So, okay. There's the funny output. Okay. But it worked. Yeah. It took 1, 2 and paired it up with 1.1, 2.2. Then it zipped up 3, 4. It took 3, 4 and paired them up and zipped them up with 5, 6. Let's see. Oh, it's hard to read. Yeah, 3, 4 got paired up with 3.3 and 4.4. Then 5.6, 5 and 6 got paired up with 5, 6, 5.5 and 6.6. The 7 here got left by alone. The 7 was the base case there. Okay, the 7 stopped the recursion right there. Okay, notice that I'm now in a land of 4 weird base cases, but they're all somehow based on this pattern up here. Yeah, it's all kind of based on this pattern here. You know, a list is either empty or something in front of a list. So I write the function to handle the empty case and the 1 item case. But then, you know, the issue comes like, what if you're pulling things out of the list 2 at a time or 3 at a time? So you can end up with, you know, kind of complicated things. Whoops. Okay. Okay. So now I'm pulling, I have 2 lists and I'm pulling 2 things at a time out of this list and 2 things out of time of that list. And then I could do really crazy things. Like in the real world, what if I wanted to pull 2 things out of the left list and 3 things out of the right list? And I wanted to create a pair here and a triple here. I could do it. It would start getting kind of confusing. But you know, if your boss tells you to write something like that because it's necessary, you know, it's not that weird in the real world to come up with kind of oddball functions like that. When people are processing data in machine learning and data science, you know, sometimes your data is in weird shapes. So you may have 2 long lists of numbers and you need them in pairs from here, and you need them in triples from here. You know, maybe these are you know, the numbers here pair up as like a first name, last name. You know, you got this long list, but they're actually first name, last name pairs. But these guys are triples of, you know, maybe uh, you know, age and address, or, you know, 3 things about a person. You know, you can actually, you know, it's coming up with weird things like this. It's not really weird. You know, they're nice puzzles, but they're also, in the real world, people do end up having to write functions like these. People would sometimes need to zip up data that's been paired up in funny ways. Okay, because the goal of this, a lot of this programming is really for data science and machine learning, where you have lots of pieces of data and you need to manipulate them. Okay, you have a file with gigabytes of little pieces of data, where the little pieces of data represent visits to a website, people clicking on things, orders. So you've got billions and billions of little pieces of data. So you have these long lists of data, and you have multiple lists of data, and you need to somehow zip them up, merge them up, filter them, do things like that. Okay, so this is good practice in that kind of a thing. And the idea is that you can take a simple function and you can just kind of arbitrarily make it a little bit more complicated and just practice with it. Okay, so zip up combined with pair up. Okay, now let's do another example. Here's an example that's going to recurse on a list and a number. Okay, so we recursed on a list by taking things out in pairs. We recursed on two lists by taking things out one at a time or taking things out two at a time. Now we're going to recurse on a number and a list. Okay, and this is another famous function, the take, and there's a companion to it, the drop. Okay, what take does is it takes in a number, and it's supposed to take that many items out of this list. So take 3 items from this list is going to give you back the first 3 items. Take 5 items from this list. Well, the list has only 3 items, so it'll give you back what's there. Okay. So the take function says, give me a number and I'll take that many items out of this list. So I'm going to recurse by counting down on this number while I'm peeling things off of this list. So here's what it looks like. If you give me the empty list, it doesn't matter what I'm taking out of it. There's nothing to take out of it. So if it doesn't matter what you take out of the empty list, you get back the empty list. Okay, that's one base case. Doesn't matter what you take out of the empty list, since there's nothing to remove, you have to give back the empty list. Another base case, and it doesn't matter what order you write these two in. If you take 0 items out of a list, you're going to get back the empty list because you're taking 0 items out of it. So I'm going to give you back 0 items. So I give you back the empty list. So it doesn't matter what was here. Okay. If you ask for 0 items out of this list, you get back the empty list. As near as I can tell, there's no importance to the order of those two base cases. They could be written in any order. Okay, so I just did the base on the empty list and then the base on the number. Okay, but I'm recursing on 2 things, so I need 2 base cases. Now, at this point, that's not 0 and that's not empty because I've gotten past both of those base cases. So I'm taking n items out of a non-empty list. Well, pull 1 item out of the list and then take n minus 1 items from what's left. Okay, there's the recursion. If I want to take n items out of a non-empty list, I take the first thing, cons it on to taking 1 less things from what's left. Okay, all right. So, and then this is generic polymorphic because this is an integer, obviously, but it says nothing about what kind of list is over here. That could be a list of anything. See, it doesn't really say what that list is. So it's a polymorphic function on the second parameter. It's polymorphic on the second parameter, not the first parameter. Oops, didn't copy. I still got this one broken key on my keyboard. Okay. All right. So notice the function takes in an integer and a list of A's. So it's polymorphic in the list, and an integer is an integer. So it's still a polymorphic function. Okay. And if I take 3 items out of the list, oh, what did I type wrong? Oh, I got the parentheses and the square bracket in the wrong order over here. Okay, notice the ML is goofed up now. ML doesn't really, the semicolon didn't get met, it didn't really notice the semicolon because it's got an unbalanced parentheses and a bracket. Now, Another semicolon may get it out of this. Yeah, it got out of that. It gave me an error message. Okay, and I can use the history list to go back, and I need to reverse the order of the square bracket and the parentheses. Okay. Okay. So there I took 3 items out of that list. If I take 23 items out of that list, I'll just get back the whole list. Okay. If I take 0 items out of that list, okay, I get the empty list. Okay. All right. So there's recursing. I need 2 base cases because I'm recursing on 2 things. I'm simultaneously recursing on the integer while I'm recursing on the list. And notice that I don't have a base case. What I don't have, I mean, I could, let me just, you might think that I need a base case that says take 0 items out of the empty list, but I don't. I don't really need that base case because it's handled by both of these. I mean, it'll be handled by this one before it's handled by this one, but it doesn't matter what order I put these in. I don't need that as that's not really my base case. I mean, it won't be wrong to put that in there, but an experienced ML programmer would notice that it doesn't need to be there. That's not really the important, that's not really the right way to think about it. I don't stop. I'm not likely to use that. I would only have that base case if I did something like, the only way you get that base case is if you take 3 items out of a 3-item list. See, that'd be the only way that you would get to 0 base case on an empty list. So this is actually not really all that useful. The only way you'd hit that base case is if you took n items of a list of n items, because then this will recurse 2 items out of a list of 2, 1 item out of a list of 1 item, 0 items out of an empty list. Okay, so this is actually not very general. You're more likely to hit this base case or this base case, where this is the base case you get when you ask for too many things out of the list. If I ask for 17 things out of a 5-element list, I'm going to hit this base case. This is the base case you get when you ask for fewer things than are in the list, which is the usual base case. I want 5 things out of a list that has 20 items in it. Then that's this base case. So this is when n is less than the length of the list. This is when n is greater than the length of the list. This would only be when n is the length of the list, which is not very, which is pretty, that would be the rare base case. How often are you going to take 3 items from a 3-item list? That's usually not how you would use to take 3 items from a 3-item list. You're almost always going to be you're usually going to be using it taking fewer items out of a longer list. See, it's usually taking fewer items out of a longer list. Okay, so it takes a little bit of practice to get used to these base cases. This one's not wrong, but it's not needed. Okay, these are really the core base cases, and it's important to understand when you get them. This is from taking more items than there are in the list, and this is from taking, let's see, which I do right. This one is, yeah, more items than there are in the list, and this is taking fewer items than there are in the list. Okay, then you hit this base case. Okay, all right. Then drop is almost exactly the same thing. Drop just says drop the first n items from the list. So it's very, very similar kind of a function. It's a little bit different, but yeah, it's got 2 base cases the same. And then maybe on Wednesday, we'll do this one example here, flatten, because it's another real famous function. Flatten is a function that's it's built into ML, it's built into JavaScript, it's built into Python. So on Thursday, we'll start with flatten because it's such a famous case and it's kind of interesting. And then we'll start talking about what's in chapter 9. Okay, there's a reading assignment for you to start reading the next chapter. Remember, the main thing in this chapter is this idea of, really important idea of higher order functions. Okay, so we're going to start talking about what we mean by higher order functions. Okay. All right. So on Thursday, we'll start with flatten, and then we'll start talking about higher order functions. And if you have questions about the homework assignment, come to office hours or send me an email. And remember, these examples are the patterns you need to do the homework assignment. Almost everything in the homework assignment is a recursion that looks something like one of these. Okay. Recursion on two lists, recursion on an integer in a list, these kinds of patterns. These are the patterns that are in the homework assignment. So look these over real carefully and try to use them as like a dictionary or as a template for how to do the ones in the homework assignment. Okay. So anybody got a question? Any last question? Okay. So we'll go ahead and quit now. And so meet again on Thursday. Bye-bye.